Good morning, students. So last lecture we discussed, just we started with wave optics and we discussed about Huygens principle. Now from the Huygens principle, we will explain refraction and reflection phenomena. The refraction and reflection phenomena is already discussed in ray optics, but that approach was different. And today's lecture, we discuss again refraction and reflection using Huygens principle. You know that Huygens principle explains how wave propagates in terms of wavefront. That we discuss. And he is the man who proposed light as the wave. Light as the wave, not the ray. In last lecture, we discussed that if wavelength tends to 0, then we can apply ray optics. But when we consider wavelength, we have to use wave optics to explain certain phenomena. So, refraction using Huygens principle. We know that refraction is taking place while rays travel from one medium to the other medium having different refractive index. So, here I have medium 1 લઉં છું. And here I have medium 2. So this is the boundary. Okay. In first case, I take this is the rarer medium and this is the denser medium. So આપણે જાણીએ છીએ in rarer medium, suppose velocity I say V1 and in velocity V2 in the medium 2. So naturally we know that V1 is greater than V2, where V1 is the velocity of the light in medium 1, V2 is the velocity of light in medium 2. V1 is greater than V2. Okay. So this is the boundary on which parallel rays are incident. A parallel ray બતાવે છે. I have shown only two. So one ray A1A incident at an angle I. I angle incident થાય છે. We know the angle of incident is always normal with respect to the normal. And AB શું બતાવે છે? Plane wavefront. AB is the plane wavefront. A1A is the direction and AB is the plane wavefront. તો A અહીંયા આગળ કોન્ટેક્ટમાં આવી ગયો છે કોઈ સમયે. Okay. તો A અહીંયા છે, B જે છે એ તો આગળ મૂવ થશે because it is in this rarer medium માં છે. તો B will reach to C, suppose the time is taken tau. Time taken to reach from B to C is tau. Then what is BC? So velocity into time. So velocity અહીંયા કેટલી છે? V1 છે in this first medium. Okay, so V1 into tau અહીંયાથી અહીંયા સુધી પહોંચવામાં લીધો છે. Then what happens to the A? A નું શું થશે? So wave emitted from A and it is always spherical wavefront. Point like object તરીકે વર્ક કરે, point like source તરીકે use કરે according to Huygens. તો આમાંથી spherical wavefront emit થશે. તો A માંથી emit થયેલું wavefront D પાસે પહોંચશે. How far is D? આમ તો સર્કલ માં ડ્રો કરવાનું. કેટલા રેડિયસ નું? તો કે V2 tau જેટલા સર્કલ નું રેડિયસ નું. V2 tau જેટલા રેડિયસ નું I draw the circle. So that is the wavefront emitted from A. એમી થયેલું wavefront છે dotted. તો AD મારું કેટલું થાય? AD must be equal to V2 into tau. બરાબર, અહીંયા સુધી સમજાણું? આમાંથી એમિટ થયેલું D પાસે પહોંચ્યું, B પાસે નીકળેલું C પાસે પહોંચ્યું. Both are reaching at the same time. D અને C પાસે એક સાથે જ પહોંચે છે. અહીંયાથી અહીંયા પહોંચતા tau, B થી C પહોંચતા પણ tau. તો AB જો સેમ ફેઝમાં હોય તો D and C must be in same phase. તો હું આ પોઈન્ટને જોઈન્ટ કરી દઉં. તો DC is my new wavefront થઈ ગયું. અને જો આમાંથી મેં વેવ અહીંયા પહોંચ્યું છે, આ જ્યારે અહીંયા પહોંચ્યું છે તો અહીંયા પહોંચ્યું છે. સોરી એમ નહીં. આ અહીંયાથી પહોંચે અહીંયા પહોંચ્યું હોય, આમાંથી અહીંયા પછી અહીંયા પહોંચ્યું હોય, આ અહીંયાથી ત્યાંથી પછી અહીંયા પહોંચ્યું હોય અને આ ડાયરેક્ટ અહીંયા પહોંચ્યું હોય. કે તમે જુઓ આ ડિસ્ટન્સ ઓછું છે અને આ ડિસ્ટન્સ વધારે છે. સો all the point on DC are in same phase. So DC is your new wavefront. DC is your new wavefront. So DC is new wavefront at time tau. Okay. AB મારું old new wavefront હતું 0 ટાઈમે અને tau ટાઈમે કહીશું DC. Shape is not changed. You can see it. AB અને DC ના shape બદલાણા નથી. અહીંયા બી plane wavefront છે. Here also it is plane wavefront. Okay. But you can see that this angle is now R. Angle of incident is R, angle of refraction is R. અહીંયા જો R હોય તો આપણે અહીંયા R prove કરી શકીએ. We can prove it. Here is also R. અહીંયા જેમ I તો અહીંયા બી I, તો અહીંયા R, તો અહીંયા હું R prove કરી શકું. કરી શકાય. This is your I. And again I have to draw the normal. So this is your R. તો આ R થઈ જશે. Now we take sin I. Sin I is equal to what? So sin I opposite BC upon AC. BC upon AC. BC upon AC. Similarly sin R. તો sin R તમે જુઓ તો શું થશે? Opposite AD upon AC. AD upon AC. AD upon AC. What is VC? તો કે V1 tau. Sin I is equal to BC upon AC. BC is equal to V1 tau upon AC. And after this is equation number 1. And in other triangle, sin R is equal to AD upon AC. And AD is equal to V2 tau. V2 tau upon AC. It's equation 2. Okay. V2 tau upon AC. Equation 2. We want to prove Snell's law. So Snell's law એટલે શું? Sin I upon sin R. તો મારે શું કરવું પડે? I have to take the ratio 1 to 2. So taking the ratio of equation 1 and equation 2, what we will get? So this equation upon this equation. So we write it over here. Sin I upon sin R equal to V1 tau upon AC divided by V2 tau upon AC. This AC cancel out. This tau is also cancel out. So we get V1 upon V2. Okay. But velocity is always inversely proportional to the refractive index. And this is the absolute reflective, not the relative, absolute refractive index. Because we know that V is equal to C upon N. C is constant. So we can say that V is proportional to 1 upon N. So if you use this relation, then V1 upon E2 becomes N2 upon N1. V1 upon V2 is equal to N2 upon N1. But wavelength is proportional to velocity, or velocity proportional to wavelength. Frequency is constant, as you know. Frequency is the property of the source. Frequency is the property of the source and wavelength is the property of the medium. So frequency तो बदलावानी नहीं, मतलब wavelength बदलाए. So finally we get this relation N1 sin I is equal to N2 sin R. N1 sin I is equal to N2 sin R. So this is our Snell's law. We use Eisen's principle to derive this. Okay. અહીંયા મેં લખ્યું છે wavelength can be changed by changing the medium. Velocity can be changed by changing the medium. But frequency, no, you cannot change it. Frequency is source માંથી જે આવી ગઈ તે આવી ગઈ. It cannot be changed. Wavelength is changed. Velocity is changed. Okay. Now one more thing I want to point it out. That is the in figure. You see this angle is I and this angle is R. And it is obvious that I is greater than R. Can you see it? Why? Because AD is less than ABC. Why it is so? Because V2 is less than V1. Why v2 is less than v1? Because this is velocity for denser medium and this is the velocity for the rarer medium. So આપણે જાણીએ છીએ કે when ray enters from rarer to the denser, it moves toward the normal, and you can see it moves toward the normal. It moves toward the normal, deviates toward the normal, rather you say. It deviates toward the normal. ક્યારે? Rarer to denser માં જાય ત્યારે. So if we have been asked, explain HUYGEN principle while ray travels from denser to rarer, then क्या हमारे चेंज करवा पड़શે? rarer to denser ને બદલે એમ કહેવામાં આવે denser to rarer જાય ત્યારે હાઇજન્સ ના પ્રિન્સિપલ થી રિફ્રેક્શન એક્સપ્લેન કરો. explain refraction. Then no change in the theory part, as it is complete, no problem. But you have to make change here in figure. તો અહીંયા જે AD મારે નાનું બનાવ્યું મારે મોટું બનાવવું પડશે compared to BC. તો જ્યારે હું મોટું બનાવવા જાય, suppose I am making like this, હું આવી રીતે બનાવવા જાઉં, keeping the A as the center, then my tangent is not here, DC, tomorrow D અહીંયા ક્યાંક આવી જશે. This is my DC, suppose. This is DC. It must be no perpendicular. This must be perpendicular. Okay. તો મારો રે ક્યાં આવશે? અહીંયા આવશે. Instead of going in this direction, it goes here. So now this is my angle of refraction. This is my angle of refraction. And you can see that in this case, R is greater than I. Why? Because V2 is greater than V1. So what happens now? So ray હવે ક્યાં જશે? Away from the normal. Toward the normal. જો denser હોય તો, અને આ જો rarer હોય તો away from the normal. So that is also I shown in this figure. I maybe, oh sorry, it is not here. કોઈ વાંધો નહીં. But you can draw this. આ બ્લુ લાઈન મારે કાઢી નાખવાની છે, આ લાઈન કાઢી નાખવાની છે, મારે બ્લેક લાઈનને કન્સિડર કરવાની. Explanation as it is. It means you can explain both the cases while it moves from rarer to denser or denser to rarer. Don't worry. Explanation same. Just you change the figure. Just change the figure. મારે D અહીંયા લઈ લેવાનું છે, બાકી બધું એનું જ. And you can say that R is greater than I, V2 is greater than V1. So it deviates away from the normal. Okay. તો આ વાત પૂરી થઈ ગઈ. હાઇજન્સ પ્રિન્સિપલથી રિફ્રેક્શન ફિનોમિના એક્સપ્લેન કરવી. So next topic is reflection phenomena using Eisen's principle. So here we have, this is the reflecting surface. Suppose I say LM is your reflecting surface. And ray is traveling in the direction of AA1, which makes an angle of incident I. So I is equal to angle of incident. Okay. V, suppose I say velocity of light in a given medium. Okay. So this is one wavefront. I say A1, not AA1. So AB is the wavefront. AB is the wavefront. A is in contact with LM and B is still is in the medium. So B થી અહીંયા સુધી આવી જશે આ wave. This will come over here. This will come over here. Okay. This will come over here. So BC. So we can say that BC is equal to velocity into time. What is tau? Tau is the time taken by wave to travel distance BC. BC જેટલું ટ્રાવેલ કરવા માટે લીધેલો ટાઈમ છે. So VT is, you can say, BC. Now what happens when B spherical wavefront emitted from B reach to C? તો એનું શું થશે? Because it is a reflecting surface. So B A is again emits the wave emitting, and you will get wave like this, and it will be in spherical shape. In 2 dimensions it is circle, but actually it is spherical. Okay. Medium is same, and therefore the radius is also Vt. So radius of spherical wavefront is equal to V tau. It will be right. So all the points on this wavefront are in same phase with C. આ બધાના phase તો same હશે જ. એ C જેટલા છે કારણ કે B અને A ના phase same હતા. તો A માંથી emitted થયેલો wave અહીંયા પહોંચ્યું અને from B it reached to C. So naturally this all points are in phase with C. So if I draw the normal or tangent, I draw the tangent, not normal, tangent to the sphere. આવું થશે. This is the normal. And this is the, you can exactly નથી દોરાણું એટલે થોડું એવું લાગે. I try to draw it. This is okay. Yes, now is right. હજી exact હું draw કરું તો થોડો ફેરફાર થશે. But this angle is 90, this angle is 90, and A to D suppose I say, so AD is equal to also V into tau. So here triangles ABC and triangle ADC are congruent. Why congruent? In 90-90, AC is the common and AD is equal to BC. And you know that when such conditions satisfy, you can say congruent. And therefore, suppose this is I and this is the, actually થોડો ફેર એટલે this is R. Okay, ચલેગા. This is normal, this is R. So if two triangles are same, naturally I and R કેવા હશે? Same હશે. I and R કેવા હશે? Same. Therefore I is equal to R. We can prove it. If this is I, this is I, this is R, તો આને હું R કહી શકું. અહીંયા R હશે તો આ બી R હશે, અહીંયા I હશે તો અહીંયા I હશે. સમજમાં આવ્યું? Geometry is nothing more than that. So you can see that using the Huygen's principle, we have shown that angle of incidence is equal to angle of reflection. Angle of incidence is equal to angle of reflection. તો Huygen principle પણ આપણને રિફ્લેક્શન અને રિફ્રેક્શનની ફિનોમિના એક્સપ્લેન કરે છે. And based on this discussion, often question is asked, what will be the shape of the wavefront after passing through certain optical device? તો એના માટે હું એક્ઝામ્પલ તરીકે લઉં કે સપોઝ I have one prism. I take prism. This is the biprism. And a ray, parallel ray is incident over here. These are the wavefronts. કેવા છે? Plane. એ અહીંયા આગળ incident થાય છે. So what is happening here? અહીંયા કેવા પ્રકારના બનશે wavefront and how wave deviates, બંને તમને information મળી જશે. So this wavefront is incident over here. અહીંયા incident થયું. So this part had already entered in the glass, but still this is not entered in the glass. So આની velocity વધારે હશે, and therefore when it comes over here, તો આટલું distance ઓછું cover કરશે. તો આ બંને point કેવા હશે? Same phase માં હશે. Then this enters in the lens, so same distance again cover. Then it comes out from the air, and still it has to travel in the glass. તો આટલું ડિસ્ટન્સ કવર કરે તો આને વધારે કરવું પડે. તો વધારે કરવું હોય તો શું થઈ જવું છે? આમ થઈ જશે. This both are in same phase. This both are in same phase. તો તમે જુઓ આવી રીતે વેવ ફ્રન્ટ બની જશે. તો રે આવ્યું અને વેવ ફ્રન્ટ if I draw normal line which show the ray તો એ આવું થઈ જશે. So when a ray enters here, it little bit deviates actually, little bit deviates, and then again it deviates. So you can trace out the path of the ray using this principle. તમને બહુ કોમ્પ્લિકેશન્સ લાગતું હોય તો બહુ ચિંતા નથી કરવાની. You know already ray optics. તમે રે ઓપ્ટિક્સ ઓલરેડી જાણો છો. તો તમારે શું કરવાનું છે? જો આમ કરવાનું છે. પહેલા મારે રે ડ્રો કરી દેવાનો છે. વી નો સપોઝ ધીસ રે ઇઝ ઇન્સિડન્ટ ઓવર હિયર. ત્યારે આવું થયું છે. તો આપણે એનો ટ્રેક કેવો હોય છે? આમ થઈ જાય છે. યસ. પછી આવો થઈ જાય છે. યસ. હવે આને મારે શું કરવાનું છે? જસ્ટ યુ ડ્રો ધ નોર્મલ લાઇન્સ, પ્લેન વેવ ફ્રન્ટ. તો અમારે લાઈન ડ્રો કરી કાઢવાની. આવું હોય તો આવું થઈ જશે. સમજમાં આવ્યું? અંદર કેવું હશે? આને પરપેન્ડિક્યુલર અગેન. So you can find the shape of the wavefront. Also you can find the track of the wave. This is one example. I take one more example. Suppose you have a lens. I take convex lens. And આના ઉપર parallel rays are incident. So this is parallel ray. Parallel ray. What is happening? This parallel rays are entering convex lens. So this rays will focus at the focal point, or at the focus. We know it. Okay. આ તો થઈ ગયું. હવે મારે શું કરવાનું છે? I have to draw the wavefront. તો આના wavefront કેવા હશે? It must be plane type because rays are parallel. Rays are parallel એટલે wavefront plane type. હવે આને પરપેન્ડિક્યુલર મારે શું કરવાનું છે? પરપેન્ડિક્યુલર લાઈન ડ્રો કરવાની છે. તો આને પરપેન્ડિક્યુલર આમ થશે, આને પરપેન્ડિક્યુલર આમ થશે, આને પરપેન્ડિક્યુલર આમ થશે. તો આમાંથી આવા શેપ બની જશે. So this is the old wavefront, this is the new wavefront. So likewise you can draw for anyone. Just first you draw ray diagram and then draw wavefronts. Wavefronts are always perpendicular to ray direction. આવું કરી નાખવાનું એટલે તમને તરત જ ઇઝીલી આન્સર મળી જશે. એનર્જી ઓલવેઝ પ્રોપેગેટિંગ perpendicular to the wave front. એવું બી આપણે લાસ્ટ લેક્ચરમાં કીધું. એનર્જી પ્રોપેગેટ્સ perpendicular to the wave front. કોઈ પણ ડિવાઇસ માટે આપણે એવું ડ્રો કરી શકીએ. Is it clear? Okay then. Next one is a very small topic, that is the Doppler effect. And I'm sure you know the something Doppler effect. It is already discussed in sound waves. Doppler effect. When a source approaching listener, frequency increases. When it receding, frequency is decreasing. So when ambulance approaching us, sound is shrilling, and when ambulance leaving, it is flatter. This is because of Doppler effect. And in that case, we already mentioned that velocity of the source or listener is very less compared to the velocity of the sound. અહીંયા આપણે વાત કરવાની છે ઓપ્ટિક્સની. So we are talking about the visible light, Doppler effect. And it is very important tools to find whether celestial objects, stars are going away from us or it approaching us. We can find out. સ્ટાર દૂર જતો હોય કે સ્ટાર નજીક આવતો હોય તો આપણે એ શોધી શકીએ છીએ. ઓકે. So suppose you have a star here and here is the observer, we all. Okay. If star is stationary and emits one wave, so whatever the interval between the two wavefront same is observed by the observer. So here suppose I say t, time period between two successive, I say suppose wavefront or whatever, here also t. Pulse સાથે જે કંઈ કરે છે frequency here, periodic time t, here also t. But if it is receding from us, if here time period is t and here time period is t prime, so this time will be greater than, it will be more, it takes more time કારણ કે એને થોડું વધારે distance cover કરવું પડશે. And because of that, if periodic time is less, then frequency is greater than frequency. So frequency, I say mu, here is equal to mu prime. So mu prime will be less than the mu if star is receding from us. Because it takes more time. When we observe it, it looks like it takes more time because it has to travel more distance. And because of that, if you say the wavelength, then wavelength, whatever the originated here, it is less than this one. So you see more wavelength. And because of this center part of the spectrum, તો તમને એમ spectrum એટલે શું એ વાત કરી દો થોડી. So when a light is passing through the prism, you are finding 7 colors. It is called spectrum. It is called spectrum. Vibgyor. You must be knowing this. Central part of the spectrum shifting toward higher wavelength. Higher wavelength. And we know that which has higher wavelength? The red has more wavelength than the violet. We know. So what is happening? When star is moving away, then you get higher wavelength. It is higher wavelength toward the red, so it is called red shift. It is called red shift. એનાથી ઉલટી વાત કરીએ. If star is approaching us with whatever some velocity, then time this is greater than t prime. We see less time, original time karta. So velocity frequency is less than frequency observed, and therefore wavelength is greater than wavelength observed. So now instead of toward, it is toward high, it is toward the less frequency, less wavelength. And less wavelength means toward violet. So this is called generally blue color no use karelo hoy છે. So it is called blue shift. So it is not actually violet, but the word used is blue shift. Blue is also, it is comparison with the blue. So it is called blue shift, not the violet shift. It is called blue shift. Moves toward the blue color. Moves toward the blue color. So red shift, well, star is receding, and when star is approaching, it is blue shift. Okay. So what is the change in the frequency? So change in the frequency is suppose mu, change in frequency. And original frequency is mu. Okay, then we can show that delta mu upon mu is equal to minus V radial upon C. This is, we have taken ready-made formula, no derivation. No derivation. Here is very important word, radial velocity. What is the meaning of that? It is not necessary always star is going to directly toward away or approaching us. It may making certain angle. So this is the angle and we are here. So this velocity has two components in this case. So this is called V radial and this is T tangential. So there is no change in the frequency because of tangential velocity. હું અહીંયા ઉભો ને આમ જતો રહેતો ફેર નથી પડતો, આમ જાય તો નજીક આવે તો. So you have to use this component, not this one. Okay, be careful. So this is V radial. Now see, you know the velocity of the light. This we can prove that delta mu upon mu, you can show that minus delta lambda upon lambda. How? We can prove. So you have to prove using this frequency f is equal to, C is equal to f lambda, use karo and you prove this. આ તમારે prove કરવાનું છે આમાં ત્યાંમાં. So what we get? Delta lambda upon lambda is equal to V radial upon C. So if delta lambda is positive, means redshift, V is taken as positive, means receding. So receding velocity मारे positive लेवानी, याद रखजो. And if delta lambda is negative, then it is called blue shift. और blue shift एवो शब्द वापरे तो negative લઈ લેવાનો આ. And velocity is taken negative and it is always approaching. Approaching velocity mare kevi levani? Negative. Receding velocity you take positive. If star is going away, so without notice you take that positive velocity. Star is approaching, you take negative. If it is blue shift, then it is negative delta lambda. If it is red shift, then positive delta lambda. So it is very interesting actually. આડું ગોઠવાયેલું છે તો આ બહુ યાદ રાખી લેજો સરખી રીતે સમજીને, એટલે યાદ તો રાખવાનું કારણ તો સ્પીડી આન્સર આપ્યું. અધરવાઇઝ યુ હેવ ટુ એનાલાઇઝ એવરી ટાઈમ. ઇફ વી ડોન્ટ હેવ ધેટ મચ ટાઈમ ઇન ધ એક્ઝામિનેશન હોલ, તો થોડી વસ્તુ યાદ રાખેલી છે તો યુ કેન ડુ સ્પીડી કેલ્ક્યુલેશન. Okay, based on that we have one problem, that is illustration 1. So here you can see the what is speed should be galaxy move with respect to us, so that the sodium light at 589.0 nanometer observed at this. So you can say delta lambda is equal to 589.6 minus 589.0. So it is 0.6 nanometer. And it is positive. So velocity of the light I take 3 into 10 raised to 8 meter per second. Exact value up here, ठीक है. Otherwise you take this meter per second. Nanometer I convert into meter 10 raised to minus. And what is the wavelength? So originally this much. So wavelength is equal to 589.0 into 10 raised to minus 9 meter. So what is your formula? So delta lambda, we have delta lambda upon lambda is equal to V radial upon C. Therefore, V radial is equal to delta lambda into C upon lambda. So we put all this value 0.6 into 10 raised to minus 9, 3 into 10 raised to 8 upon 589 into 10 raised to minus 9. અહીંયા ના કન્વર્ટ કરે ચાલે ખરા because it is a ratio. So you simplify this, so that comes out to be 306 into 10 raised to 3 meter per second. It means that 306 kilometer per second. Okay. Here velocity is taken to 3.06. એટલે એમાં થોડો ફેરફાર આવે તો કોઈ ચિંતા નહીં કરતા. So this is the velocity of the galaxy, and it is away because it is positive. Away means positive. Okay. When monochromatic light is incident on a surface separating two media, the reflected and the refracted light both have the same frequency as the incident wave. Explain why. So it is actually not the calculative base, but just you have to explain. So whenever light is incident over here, so this light interact with the atom on the surface. An atom, you know that it has electrons, so electrons are oscillating. It oscillate. It is called force oscillation, depend on the frequency of the incident light. And when it oscillates, again it emits the radiation of the same frequency. So whatever the frequency of the incident, with same frequency this oscillate, with same frequency it re-emits. Okay, so frequency don't change. Same thing is happening for the refraction also, because whatever the light emitted, it is ignited to the other atom and so on. So frequency ક્યારે એટલે બદલાતી નથી. When light travels from a rarer to a denser medium, the speed decreases. Does the reduction in the speed imply a reduction in the energy? No, it is not at all. Speed is not related with the energy. Speed is totally separate thing. Energy is, you can say that energy pass, intensity means energy passing per unit area per second. Intensity is equal to energy passing per unit area per second. Okay, so energy is related with the amplitude, it is not related with the velocity. The velocity depends on refractive index, so no. In the wave picture of light, intensity of light is determined by the square of the amplitude of the wave. What determines the intensity of light in the photon picture? So yes, this is already mentioned here, it is proportional to amplitude. It means energy amplitude square છે actually, પણ મેં amplitude just બતાવ્યું હતું, exactly amplitude square છે. તો વેવ નેચરમાં શું છે? નો, નોટ લાઈક ધીસ. સોરી, ઇન પાર્ટિકલ નેચરમાં આવું નથી. તો એમાં શું છે? તો દેટ ઇઝ ઓલરેડી ઇટ ઇઝ ડિસ્કસ ઇન ચેપ્ટર ડ્યુઅલ નેચર ઓફ લાઇટ. પણ થોડી વાત કરું તો મોર ઇન્ટેન્સિટી મીન મોર ફોટોન્સ આર કમિંગ, બીકોઝ લાઇટ ઇઝ મેડ ઓફ ધ ફોટોન્સ, મોર ફોટોન્સ. સો મોર નંબર ઓફ ફોટોન્સ આર ઇન્સિડેન્ટ. તો એના કેસની અંદર એવું કહી શકે એનર્જી ઇઝ ઇક્વલ ટુ NHF. મોર નંબર ઓફ ફોટોન્સ આર ઇન્સિડેન્ટ. વેવ નેચરમાં એકોર્ડિંગ ડિપેન્ડ ઓન એમ્પ્લિટ્યુડ, અને પાર્ટિકલ નેચરમાં નંબર ઓફ ફોટોન્સ, અને ડિવાઇડ બાય એરિયા કરી નાખીએ અને ટાઈમ કરી કાઢીએ, ડિવાઇડ બાય એરિયા એન્ડ ટાઈમ કરી કાઢીએ, you will get the intensity. So more number of photons are incident means more intensity. In wave nature, more amplitude, more means more intensity. So particle nature, in particle nature, more number of photons. And in wave nature, more amplitude. Okay, thank you very much. We will discuss now in third lecture.